So just real quick, so our company, we're basically a climate information company. So there's InsurTech, AgTech, FinTech, and we like to call ourselves ClimTech. And so we're doing crop yield forecasting, long range forecasting for forecasting weeks and seasons in advance, and then an effort around climate change and understanding climate change related risks. So first off, I have to disclose there's a lot of graphs in this presentation. Some slope down and to the left, or down and to the right, and some slope up and to the right. And unfortunately, when we're talking about changes in the climate system, it's hard to avoid the time axis. And so briefly, we're going to talk about just a little bit about what's changing, which is to say what we know is changing. We're going to talk about physical climate risks. So there's two kinds of climate risks. Well, there's many kinds of climate risks, but one is physical climate risk, and the other major one is a transition risk. So a transition risk is the risk that there's some significant legislative action that changes the landscape dramatically, and you might have stranded assets or something along those lines. So I'm not talking about that. I'm not talking about legislative risk either, but more physical risks of what physically might be impacted by climate change. We're going to talk about an indicators of one of the specific risks. So I don't have much time, unfortunately, so I have to limit scope a little bit. And then we'll talk about implications for the future and for modeling risk. So a changing climate should come as no surprise, is changing many aspects of society. A lot of it is based on changes in temperature and changes on precipitation, which is what I'm going to talk a little bit now. So first we're going to go to central England. Why are we going to do this? So it turns out there is a temperature record in central England that is the longest known recorded temperature history on the planet. It goes back to the 1700s. We're going to end up looking at data from 1878 to today, and that's because they're starting in the late 1800s, there was enough data to be able to do some quality control and trend analysis on the information. And so as I say, it's no means perfect, but it certainly can be considered representative. So if we look at annual average temperatures from this time series from 1878 up to, that is literally like a couple of days ago when I generated the graph, we see there may or may not be a trend depending on how you look at it. You can fit a trend to it statistically quite easy. And so it turns out there is a trend here. It is about a degree over this time period. But we can see that the variation is by no means continuous, and that the variability at this particular location is relatively large. And so in general, when you go from a large area like the Northern Hemisphere to any individual point, the year-to-year variability always increases because you're getting into microscale effects and finer and finer impacts. So we can take that time series and we can layer on a product from NASA, so the NASA GISS time series. This is the time series that shows up in the news an awful lot. And what I find interesting about this Northern Hemisphere temperature is if we're looking at the anomaly relative to an average time period, the broad pattern is roughly the same. So there's a warming period, a cooling right around the 1950s, and then a warming again from about 1970 on. And so what's interesting is that, so this individual point represents some of the variability and some of the change that has occurred within the Northern Hemisphere. I apologize, I realized this morning, oh, good, okay, sorry, I'm gonna apologize on the next one. So that same NASA product, we can look at temperature changes in the United States, and we see again that the broad change is roughly similar. So the changes in the Northern Hemisphere are all gonna be roughly similar in terms of the pattern over time. But the variability from year to year will be increasing or decreasing based on the specific location. And so finally now we're going to look at all three. And so we see that the Central England time series in red, the Northern Hemisphere time series in green, and then the USA average in blue. And so this is where I apologize for changing the colors. I didn't realize I did that until this morning. But again, the pattern is all roughly the same. So what is the impact then for the United States? So we're going to look at annual temperature in this case. We also see winter changes and summer changes. And so this happens to be, it's an average from the early part of the century, from the latter part of the century. And so I just highlight here, in the graphs we were just looking at, we're differencing these two yellow periods to get a sense of the change. And so the result is that temperature is changing. Hopefully it comes as no surprise. I know in my own experiences, I can see changes in temperatures, but the change is not consistent from season to season. But there's no doubt that there is temperature changes. So one of the things that you can do then is look at other parts of the ecosystem that are impacted by temperature changes. So on the left-hand side, this is the annual global change in glaciers. So it's the mass of glaciers on the Earth. So the red is a loss of mass, and the blue is a gain in mass over time. And then the right-hand side is basically the sum of the individual years. And so we see that in general, our glaciers are losing mass. So this is the idea, right, is that in general, water melts at 32 degrees. And so if the freeze level is changing in the atmosphere, we're going to lose ice in general. And so I'm going to comment on this later, but this has important implications for hydro generation because quite a bit of hydro in the United States and in the world is based on snowmelt and snowpack melt. And so there is risks associated with changes in the potential for hydro generation based on temperature changes. We can go further and then look at individual changes in terms of different regions around the world. What I find striking about this graph is the orange line on the bottom is the United States. And so glacier loss and water loss in a frozen form as a resource is decreasing most rapidly in the United States. So what does this actually look like? We can go to Glacier National Park, and we see two photos of the Grinnell Glacier, one from 1928 and one from 2008. I now realize I have reversed the pictures, so I apologize for that, but I think you get the point. In the black and white photo, there's a massive amount of ice here on the glacier, and if we look then at the 2008 photo, it is virtually gone. And so just in terms of this order of scale, I don't know how far that drop-off is in the background, but we can see that it's completely filled with ice in 1928. And so that's an example of the loss of ice mass in a glacier that, again, here is at Glacier National Park in the United States. So we can also look at other data. So it turns out the Blue Hill Observatory in Massachusetts has the longest known observed temperature record in the United States. They also do records of dates when blueberries ripen. What this chart says is blueberries are ripening on average earlier. And so there's lots of changes like this that have been recorded in the academic literature of things like blueberries ripening earlier, the summers last longer, fall is extending further into the year. And so much of the things that depend on temperature for growth are changing their cycles as the temperatures change. And so I show this just as an example of, not that it matters for this industry, but that much is being impacted by the changes occurring in temperature. So the temperature change then, turns out, has an important implication for precipitation. And so what I want you to do is think about a hypothetical daily rainfall distribution. So that's the blue curve here. So for rainfall, there can be no negative rain. So this distribution has no negative values. And generally speaking, when it rains relatively small amounts, many times. And extreme rainfalls are generally rare compared to looking at all of the rainfall. And so there is an idea that what's happening is that when it rains, it's raining more in general. And so this distribution is changing. The tails of the precipitation distribution are becoming fatter. And so it turns out in 1998, there was a paper published in which long time series from weather stations across the United States were analyzed. And what this shows is the frequency of extreme rain at this summary of many, many weather stations. And so again, this is an upward and to the right trend. And so what this graph is showing is that, in fact, our precipitation distributions in the United States are changing. So the question is, why is this occurring? So it turns out there's a fun little equation. It's called the Clausius-Clapeyron equation. In high school chemistry or physics, you may have learned about the latent heat of vaporization. It's the equation form of the latent heat of vaporization. So when water vapor goes from gas to solid, it's changing its molecular structure, and energy has to be released for it to go from a gas to a solid. Likewise, when you boil water and you put energy into the water, the molecular structure is absorbing energy so it can separate itself from the solid. But it turns out that the Clausius-Clapeyron equation shows that the amount of water vapor in the atmosphere is directly proportional to temperature, but it's at an exponential rate. So the warmer a certain parcel of air is, the more water that it can hold. And so what's happening is, as our surface is warming, there's generally more water vapor in the air. And that more water vapor then powers the development of rain. So in this case, when I say powers, I literally mean powers in the sense that the heat released from water vapor turning to water, or from water vapor turning into a cloud, is releasing heat. That heat warms the air. The way air rises, it cools a little bit more water is released, so on and so forth. And so incrementally and exponentially more water with a tiny little change in temperature means that there's more latent heat of vaporization in every storm. And because there's more water vapor, and because there's more energy, the storms are becoming slightly more severe over time. And the result is that when it rains harder. And it's because there's more water vapor in the atmosphere. And so the impacts on precipitation then in the United States, so this is the same time period that I showed before. So in general, in annual precipitation, it's raining harder, but we can see winter, spring, summer, and fall. And one of the things I find remarkable about this graph is, for example, the impact on the southeast United States during the fall. So that's 15% more precipitation has occurred on average over the last 20 years than occurred in the first part of the century. So you may think flooding is increasing, and you'd probably be right because, again, it's raining harder when it rains. And so just to kind of drive this home a little bit, it's a graph shown in insurance terms, but so it's 2-day precipitation events exceeding basically the 20-year the 20-year extreme rate. And so what we see is over the last 40 or 50 years, rain in the United States is becoming more extreme. So with regards to the changes being caused by a changing climate, I'm confident that temperature and precipitation together are then driving many, many other changes that occur in our ecosystems, in our mechanical systems, and that what I just talked about is like one of the fundamental changes that is occurring. So it turns out that the Department of Energy pulled together a group of folks from the energy industry, and they created what is called the Partnership for Energy Sector Climate Resilience. And they wanted to study climate resilience in the energy sector. And they pulled together 18 companies, and they did workshops and surveys and really worked through to try to understand what some of the risks are associated with climate change. And a summary from one of their reports is this table. So the table is what most concerned primarily electric utilities about a changing climate. And so we can see things like flood and precipitation changes, summer storms, extreme temperatures, average temperature, sea level rise, winter storms, and fire. So some we heard about earlier today. But so I kind of group them in general into disruptive storms, temperatures, sea level rise, drought, disruptive weather storms, and wildfires. At a very high level, those are how you can categorize risks associated with the risks associated with a changing climate. So earlier this morning, I used our friend Google. And so as an example, the sea level rise on the East Coast over the last couple of years has been 5 inches a year. And so there are assets deployed along the East Coast and along the West Coast that are certainly at risk if adaptation and mitigation steps aren't taken. And so just as an example of the kind of risk. So as an example of some of the risks associated with temperature, so increased temperatures specifically for a power plant or for an electrical network, we see that increased temperatures have the possibility of a very, very slight decline in the efficiency of power being generated. We see things like increased water temperatures of the rivers and bodies of water that are used for thermal cooling can be modified. And so an example This is a study, I'm going to guess from before Germany went all in on renewable power, but that a 3 degrees Celsius rise in Germany could result in a 36% decrease in generation capacity in Germany. So that's a pretty substantial risk associated with warming waters. There's things like decreased transmission capacity, and then there's the potential for modification of demand profiles as temperatures change as well. And that induces financial risks, capacity risks, and could be exacerbated by population. So this is a temperature profile that happens to show the relationship of electricity consumption versus temperature. I'm particularly partial to this one because it happens to be from my house. So I'm a customer of Dominion. Dominion gives me 30-minute resolution data on my power consumption. And I'm a geek, so I've been downloading it for 3.5 years. And this is the result. But what I find remarkable about this profile is it looks like every electric utility I've ever seen. Now, it changes in the extremes based on the geographic location and the climate of that location. And the reason I show this is because the modification of demand profiles are particularly at risk at the very high end. And we can see that the slope is much higher at warmer temperatures as energy is required for cooling. And so as we're shifting towards warmer climates, that upper end becomes a potential risk. So it just so happens that one of the impacts of the temperature to water vapor relationship is that the dew point is also trending positive as well. So in prior work, I managed to sell software for real-time weather software for real-time electricity trading. And we found that in the real-time markets, prices tended to go crazy after 3 days of very, very high heat index values. And so that's the direction that we're headed towards. So then in terms of identification of a specific risk, we can take a look at some NERC disturbance analysis working group data on what were the causes of power outages. So this is power outages to consumers. And we see that weather in general ranks quite highly. And then as well as other non-weather related variables as well. And so, so the idea is that the electric utilities must report disturbances that interrupted 300 megawatts or 50,000 customers or more. So this isn't exhaustive, but it is above a certain threshold. And so what we see then, again, is that the types of outages, the things that are causing outages, roughly align with what the DOE partnership showed. And then in particular, that lightning and wind and rain together would be what I would call severe storms. So one of the things that came from that study is that one of the concerns is the changing probabilities of severe weather. And so again, that changing probability is due to this temperature-water vapor relationship. So then the question becomes, does increasing severe storms create risk in the electric power system? So it turns out there have been some studies in this direction. So one is a Climate Central group. So Climate Central is a group that focuses on communicating information regarding climate change to different groups, particularly to media organizations. So they did a study that linked 2 data sets together, one which was the one we just looked at, and then a newer data set. And they conclude that weather-induced outages are in fact increasing. And there is a separate study done by the White House in 2013 that uses essentially the same data and comes to the same conclusion. So I consider this to be a bit hand-wavy at this point in terms of analysis of the data. So it turns out there's another study done by Lawrence Livermore, and they tracked data from 195 electric utilities, and they gathered as much data as they could that was publicly available for SAIDI and SAIFI, which are measures of the minutes of interruptions and the number of interruptions per year in terms of power outages. And so it's a complex technical paper. But in the end, they have a couple of graphs that are kind of interesting. So the data set includes outages that include all outages, including major events. So the big spike in 2008 there is due to a hurricane, for example. And then they also look at outages by these 2 metrics that exclude major events. But these are all, the point is these are all outages that are caused by weather. And so they built a regression model to try to understand what is driving these values. And so in this regression model, they find things that are not very surprising, like an increase in lightning, in fact, induces an increase in outages, right? So that should come as no surprise. But they also find that there is a statistically significant positive trend in satiety. So there is a trend with time in one of these outage measures. And their conclusion is that weather is changing and it is causing an increased level of outages. The same group of authors also publish a separate paper that I mentioned here, and they find that the source of the outages generally comes from the distribution system. So roughly 90% or more of the outages occur within the distribution system. And so what I find surprising about this result is not necessarily that the data shows that there's a trend, but if you go back and look at data from the EIA, overall there's been increased spending in both capital expenditures to harden the distribution network, as well as increases in operations and maintenance. So despite the fact that there's been increased spending to try to maintain the network, there's still potentially a positive trend. I actually I emailed the author and asked if there was an update, because the last set of data was 2012, and he told me that they actually have submitted a paper that updates the data through 2016, but unfortunately he couldn't give it to me until it's accepted or denied. So the idea here is that there is at least some indicator that the changing conditions are causing more outages. And that has potential long-term implications for the reliability overall of the network in a changing climate. And so we've actually seen different versions of this earlier today. So this is EIA data of US sources of generation in the United States. So coal is decreasing, which comes as no surprise. Gas is increasing, and renewables are increasing as well. And so this is a trend that is in the market, and I'm sure all of you are aware. It shouldn't be any news to you. And it is a trend that is occurring in part because of concerns around the causes of the climate changes that I'm discussing. But the reason I bring this up is to be able to tell a story. So I was at a conference earlier this year, and a gentleman by the name of Heinrich Steisdal spoke, and he is a retired CTO of Siemens Wind. And he participated in a survey of, and I should preface this by saying, I'm telling you this totally from memory of being at the conference. I emailed him and asked for his slides, so I'm gonna get it roughly correct, but maybe the details are not exactly correct. But so he participated in a survey that was a survey of what the cost of offshore wind will be over the next 30 years for these very large projects that are being built in Europe. And so the blue line is the surveyed cost of a body of experts, and then the band shows you what the uncertainty was. And if I am correct, yeah, so then the gray line is fixed offshore cost over time, and the green then is onshore. And so it's a body of experts. They surveyed on the cost. And then these projects were the bids were put out for these projects by the English government, the Dutch government, and the German government. And the yellow dots are the costs that actually got bid. Right? So this group of experts estimated what they thought the cost would be for offshore power. And then 2 years later, it was half the cost based on what the experts thought. And so the point here is that the market is rapidly changing. And it's very hard to predict from one day to the next what is likely going to happen. And so from my perspective of thinking about the potential climate risks within an electricity network or within an electric utility, I guess I would say there is a potential that by changing generation mixes, you're certainly increasing risk from the climate perspective, whether it be risks of solar generation, hydro generation, or wind generation as well. And I should follow this up by saying, interestingly, earlier this week I met with a company that they do nothing but wind power generation. So they're operating wind power assets, and they are interested in whether wind in the United States is going to change enough over the next 20 years to materially impact their business. And it's an example of the type of change that is occurring. So in summary, a changing climate creates many potential risks. to individual elements within the electricity network and potentially within an electric network or an electric market overall. And so I'm going to close by saying, while traveling here, I read what I considered to be a fascinating paper, and it was a PJM fuel capacity risk analysis. And I was reading it to try to understand what is this Plexos thing anyway. And so it was great because it laid out a complex analysis. They looked at, it was 324 scenarios of asset retirement, of natural gas pipeline outages to try to understand what are the risks for fuel supply. But it gave me a wonderful chart. So this is the study. It's actually available on the Energy Exemplar website where I got it. But there's a nice chart that shows in, I believe this is in 5 years, what the likely generating capacity by fuel type or resource type is going to be in the PJM. And so I looked at it, and there's like 3% risk associated with renewable assets, so hydro, wind, solar. And the sun could turn off, and roughly speaking, PJM would be okay. They'd be within their operating margin. But one of the risks that I mentioned earlier is this potential for a thermal cooling risk of either low river flows or warming temperatures within the bodies of water used for cooling. So it turns out that 85% of PJM's generating capacity is based on thermal. And so what I would encourage everyone to think about is the degree to which the changing environment that is occurring could be creating risks that you may or may not be thinking about. And that's it. Thank you very much. I'll say one last thing, that I find that there's always questions that people have about climate, and maybe you're afraid to ask or something along those lines. So I'm around all day. I love talking about this stuff, and I'll take questions.
We do have a few. Yeah,
great, let's do it.
Yeah. So great, thank you, Jan. First question is, does the warm and wet trend also play into events of extreme cold, or are those unrelated and separate? For instance, PJM area has 1 in 100 year extreme cold, but it's happened 3 times in the past 6 winters. So.
Yeah, so there is, the answer is yes, it does. And so really simply, why does the wind blow from west to east in the northern hemisphere? It's because there's an ice cap that is on the north, and it's cold, and it's higher pressure. There's a pressure gradient, and the pressure gradient causes the wind to flow, and the Coriolis force bends it from west to east, it turns out. But it turns out that temperature gradient from the pole to the northern hemisphere is what drives our circulation. That temperature gradient is changing, and we're starting to see circulation changes at the hemispheric level. So there is the potential that we're seeing a transition phase and some pretty crazy events because our system is transitioning potentially to a new state. So the short answer is yes, and that was the long answer.
So the jet stream could change as well.
Yeah.
Turns out the flight to the east could be shorter than the flight to the west someday.
Yeah, that's right.
Imagine that. Okay. Another one is, what energy resources would you rate as the highest priority for adapting to weather changes?
That's a great question. I will tell you that, so I think we as a society, we have a challenge in trying to find our way to a low carbon power production. Clearly anything that is relatively carbon free, whether it be wind or solar, there's no right answer other than trying to find as much power as possible from renewable resources while balancing the need for reliability as well. So that's the constraining factor.
Flexibility part.
Yeah.
Okay. One last question was on the claim about Germany's risk of a 36% reduction in capacity due to increased temperatures. Is that purely from reduced efficiency on the thermal plants, or is that also considering other factors?
No, that was a statement around the risk of warming temperatures and reduced stream flow in their ability to cool plants. Yeah.
Okay. Great. Any others that didn't make it onto the list? Okay, great.
Great.
Thank you, Jan.
Yep.
Yeah.